Hi everyone, I'm Professor Burgasser, and in this video we're going to be talking about energy diagrams, which is going to be our energy equivalent to the position, velocity, and acceleration diagrams we looked at back in our kinematics section. Now if you recall, we use these position, velocity, and acceleration diagrams to analyze the kinematic motion of an object, the 1D kinematic motion of an object. And by looking at the slope and the curvature of the line of position, velocity, or acceleration versus time, we're able to say something about the motion itself and even compute some quantities graphically. So as an example, if I take this arbitrary position versus time plot, when we look at, for example, the slope at the first part, that tells us it's a positive velocity because it's a positive slope. The change in position with respect to time is the velocity. If we look at the flat part, that means there's zero slope, so zero velocity, so that's the case where the object is stationary. And then when we look at this curved part, because it is a positive curvature, because the slope is increasing with time, that tells us that it has a positive acceleration. So this might be something where there's a force that's accelerating the object forward, and that's represented by this curved line. So each of these sort of maps of this line, descriptors of these lines, slope, acceleration, curvature, all these quantities allow us to describe the motion from a graphical perspective, and it's a very compact way of visualizing the motion itself. So can we do the same thing for energy? And that's certainly possible. So the way we draw our energy diagrams is to plot the energies, the potential, kinetic, and total mechanical energies as a function of position instead of time. Remember, all of our energy work has been looking at how forces act over a distance or a displacement, and so what we're really looking at is how energy changes along a one-dimensional path, for example. So let's take the example of a spring. If you remember, our potential energy expression for the spring is 1/2 k times the position of the object relative to its equilibrium position, or the stretch of the spring relative to its equilibrium length, squared. And that's a parabola on this curve, a parabola that's shifted so that its 0 point is at the equilibrium point. All right, so that's the potential energy. How do we write down the total mechanical energy? Well, this depends a bit on our initial assumptions. So let's say that we are going to stretch this spring to some length x and then let it go from rest. Well, on this diagram, that means that we're going to start at this position along our x-axis, and we're going to start at the point where we have zero kinetic energy, and we've stretched the string so we have all potential energy. So the total energy is just going to sit on this potential energy curve. But of course, the energy in this system, which only has conservative forces, is totally conserved, both in time and position. So the energy, the total mechanical energy, is represented by a horizontal line, and the magnitude of that initial energy is just equal to the initial potential energy, which is 1/2 k times our initial position minus the equilibrium position, quantity squared. So that describes both the potential energy and the total mechanical energy on our energy diagram. We've got one more to go. How do we describe the kinetic energy? Well, let's move over to another point on this plot. We'll call it x. And we want to see what are the energies acting here. Well, we've got our total mechanical energy, we've got our potential energy, and of course the kinetic energy is just the difference between that total mechanical energy and potential energy, right? Kinetic energy plus potential energy is total, so kinetic energy is just the total minus potential. And so what we're really looking at is the difference between these lines, and so that magnitude is just this red line that indicates the distance between these two lines. That quantity is the total kinetic energy. And of course we can just equate it to our potential energy term because we know what that potential energy expression is and we know what our initial energy is. So we can compute this for any point along the curve. We can compute it there, we can compute it there. We can compute it in the middle where we're at the equilibrium position. And of course at that point we have zero potential energy. So all of the initial energy is in the kinetic energy. And this is, of course, the place where it's going to move the fastest at its equilibrium position. Now, if we were to take all of those energies and plot them together, as you see, we would find that we would get a curve, another parabola, this time inverted. And of course, that parabola is simply because we are taking our initial energy, which is a constant, minus our potential energy, which is a function of x squared, so it's minus x squared, where the 0 point now is the initial energy, and that lies at the x equilibrium. All right, so we've got now a plot that shows the total mechanical energy, the potential energy, and the kinetic energy of the system all in one place, and all as a function of position. Now there's a few things we can start to notice about this plot. So for example, when I look at where our kinetic energy lies, you can see that at the bottom that this kinetic energy disappears at 2 positions along our x-axis. The initial position, of course, is our initial starting position where we started it from rest. But of course the other side is the maximum stretch in the other direction, right, as far as it can go. Now these 2 limits really define the allowed positions of motion, because in between here you can have a kinetic energy that's greater than or equal to 0, because the total energy is greater than or equal to the potential energy. Right? So this is an allowed region for the spring to oscillate. Outside of this, the total mechanical energy is less than the potential energy, so if I subtract those 2, I get a negative number for kinetic energy. And if you recall from our definition of kinetic energy, 1/2 m times velocity squared, that m, the mass, is positive. Velocity squared has to be positive, and so there's no way for kinetic energy to be less than 0. So this energy diagram delineates the region where a spring is allowed to reside. It can't go past these initial sort of maximum points because it's simply not moving at that point, so it can't go any further. So we're setting a constraint on the motion. Now, this is an example of a 1D spring. You can do an even more complicated example by looking at 2D motion. So in this case, this is a film that was created by a student where they combined a spring and a pendulum force, and by computing the energy, the potential energy, when the object is set from a resting position and stretched out, you can see that even though the motion is quite complicated, the bar, the mass in the middle, sort of the little bar limit in the middle there, stays within our potential energy circle. It never goes outside of its 2-dimensional constraints. So even for complicated 2D motion, this idea of constrained motion is still viable. And of course, it only comes about because you can't have a negative kinetic energy. Now, let's go back and look at our potential energy for a 1D spring and consider the forces that are acting on the spring. So if I go back to my position x, where I've computed both the potential, kinetic, and the total mechanical energy, recall that we have a force that's giving rise to this potential term, which is minus k times the displacement from equilibrium. In this case, the x value is less than the equilibrium x value, so our force is actually going to point in a positive direction. Right? It's going to move us toward the equilibrium point. Well, let's look back at the potential energy curve at this point. You can see that the slope at this point is less than 0. It's a negative slope. It's getting bigger as we go to smaller numbers. So that is an opposite case. The force is pointing in a positive direction. The slope of the potential energy curve is in the negative direction. Similarly, if I go to the other side of our motion, in that case, the x position is greater than our equilibrium position, so the force is going to point inward. It's going to point in a negative x direction. And of course, our slope is in the opposite direction, which is increasing with x. And finally, if we look at just the 0 point, of course, in that case, the equilibrium point is equilibrium because there's no net forces. But we also notice that the potential energy slope at that point, that curve, is hitting its minimum. And of course, anytime you hit a minimum, the slope disappears. It goes to 0. So there's clearly a connection between the slope of the potential energy curve and the force that's being exerted on the object. And we can see why that is by going back to our original definition for the change in potential energy, which is just the work done by conservative forces. And in the one-dimensional case, this is just the conservative force times the displacement, and of course a minus sign because it's the negative work. Now all I do is just divide this equation by delta r on both sides, and we end up with a differential form. All right, the force of the conservative force is just minus the change in potential energy divided by the displacement. Or if we make this a small derivative form, it's just the slope, ddr, of the potential energy on our potential energy diagram. So that slope term is actually equal to the force, the net force, acting on our object in this conservative force system. And that harks back to when we look at the slope of our position versus time diagram, that the slope is just equal to the velocity of the object. So we can graphically calculate the force from our one-dimensional energy diagram. Now it turns out we can do this in 2 and 3 dimensions as well. To do this we have to introduce a new operator called the gradient operator, and this is just taking the derivative along each of the coordinate axes. And so if we look at rectangular coordinate system, for example, the gradient operator is a vector, and each of the vector components is just the derivative along that component. So this is the case if we want to expand out to higher dimensions, but it's completely equivalent to our one-dimensional case, where the force is just equal to the change of the potential energy with respect to that axis. Now another thing we can look at in terms of the potential energy diagram is the curvature of this line. And you can see very clearly that the curvature is sloped positively, right? It's opening up as we go to either side. The slope increases as we move away from the equilibrium point. So the curvature is, which is the second derivative of potential energy with respect to the position, that's greater than 0. And that corresponds to a motion in which we are oscillating back and forth across this equilibrium point. Right? The object, we say, is stable around the equilibrium point. Even though it's oscillating, it may not stay at the equilibrium point very long, it always comes back to that motion. Right? That is the definition of a restoring force, which the spring force, of course, is. Now, we can take an example of a force that's not restoring, that's not stable. A good illustration of that is if we just take a pencil and try to stand it up on its end. So if I just let it go nicely, nope. Totally falls down. Let's try again. Nope. Now notice that it's never stable. It falls down and it falls down in completely different directions, and that's based on very slight displacement of the angle with respect to vertical axis. So we can write down an expression for this. We can look at the energy diagram for this by considering that the motion, the force that's acting on the pencil is just the force of gravity near the surface of the Earth, and of course that's acting on the center of the mass of the pencil. And so if the pencil is tipped over just a little bit, then it's going to be pulling on that center of mass relative to its contact point, and we can write down a potential energy for that center of mass as just the length of the pencil divided by 2 times the cosine of the angle relative to the vertical axis. And you can work out the geometry on this on your own. But this gives us an expression for potential energy as a function of the tipping angle. And if we then draw a potential energy diagram, an energy diagram of this, this is what that diagram looks like. We have a maximum at the equilibrium point, which is the point where it's pointing straight up, but then it falls off to 0 as we go to larger angle. So if we start this object at the very tip, which is at when it's standing straight up and it's got its maximum potential energy, that sets the total energy of the system. But notice that on either side we're going to have positive kinetic energy, and more importantly, the slopes of the potential energy curve are such that the force is going to always act away from this equilibrium point. So on the left side of this force potential energy diagram, we have a positive slope, so we have a negative force. On the right side we have a negative slope and therefore a positive force, and on both sides the force is driving the pencil away from its equilibrium position. So the curvature of this potential energy diagram, of course, is also negative, which is the opposite of our spring, and so this is a good example of an unstable point about the equilibrium point, an unstable motion. So clearly stability is related to the curvature of our potential energy curve. And so that gives us another piece of information graphically about the behavior of the system. Now looking at the slopes and the curvatures and the constraints that are indicated by energy diagrams is really important for studying more complicated systems other than springs. A good example is the van der Waals force, or the van der Waals potential, which is a potential energy term that describes the weak electrostatic force that bonds two atoms in a molecule. There's a part where they are attracted to each other because of their electrostatic attraction, and of course a part where they are repulsive because they run into each other. We can approximate that relatively complicated force law by just a sum of two polynomials that vary with distance away from the center of the separation. So if we have 0 be the point where they're overlapping, we have a potential that looks like the following. And of course we can start to analyze the behavior of this atomic bond, or the atoms in this bond, by just analyzing this potential energy diagram. So for example, we have places where there's a repulsive force that's keeping the atoms from coming together and pushing them apart, and we have a counteracting attractive force when they're pulled a little bit further away. And that gives rise to an equilibrium point, which is a stable equilibrium point because the curvature is positive. We can also look at cases where we can measure the total energy of these two atoms and see where they're constrained to lie. So if the energy is low enough, in this case, the way we've defined our axis, the energy is negative, then we have two atoms that are in a bound state because they're limited in the range of movement that they can separate from each other. All right, that is an example of a bond or a bonded molecule. Now if we raise the energy to a positive value, in that case we have one constraint of the motion, but on the other side there's no constraint going off to however far we want to go away. So that's a case of an bounded motion. And so that's a case where these atoms are not going to stay in a molecule, but they're just going to fly apart. And of course that's what you'd expect if you raise the energy of this atom-atom system. So there's a lot of information we can glean from these energy diagrams. Now up to this point I've only considered conservative forces because that's the case where we can write down a potential energy term. But of course we have many cases where we have dissipative forces or any kind of non-conservative forces. So we have to figure out how do we incorporate those forces into our energy diagram as well. Well, what we can do is we can consider the fact that when we have a non-conservative force, the work done by that non-conservative force changes the total mechanical energy. So let's start with my spring again. If I start it from one stretch position and I release it from rest, this is the initial energy and the potential energy. And of course we can compute the kinetic energies across this point. But if I have a dissipative term, let's say friction acting in the spring, then as the spring oscillates, the total energy of this system is going to slowly decrease as it moves down. And the amount of decrease is of course going to be equal to the work done by the non-conservative force. So as the spring oscillates to its other side, when it reaches that other limit, that limit is actually now smaller because the total energy has gone down over the course of this motion. When we come back to the other side, the energies come down again, and you can see that the position that it ends up with here is less than the initial position that I started. All right, it hasn't been able to stretch the spring as much because it's lost its energy to this dissipative friction force. And this can go back and forth. Now this is an example of a damped harmonic oscillator. And we can write the displacement of the damped harmonic oscillator as a function of time. You can see it has this same oscillatory motion that we see for our regular spring, but that the amplitudes are being squeezed as energy is lost to the system. So this is a very common example of the kind of forces that we see in our regular environment, not the idealized perfect spring, but actually springs that are being damped because of friction. And you can see we can approach this problem pretty straightforwardly by looking at the energy terms as opposed to looking at, for example, kinematics or Newton's laws. So to summarize, the energy diagrams that we've just talked about are a really effective way of visualizing the mechanics of the system and looking at how that system changes both with time and position. We simply can write down the potential energy term based on our expressions for our conservative forces. We can write down our initial energy, and from those two terms we can calculate the kinetic energy at any point in our system. This also provides a way of constraining the motion, measuring the constraints of the motion, seeing where the kinetic energy goes to less than zero. An object can't be in those regions, so that sets our limits for the motion. That gives us bounded motion. We can also look at how the conservative forces are actually expressed by simply computing the slope of the potential energy term, because that's how we've defined our potential energy in the first place. And finally, we can look at the curvature of our potential energy expression, and that gives us an idea whether the motion is stable or unstable. A positive curvature potential energy expression gives us a stable motion, and a negative curvature gives us unstable motion, like the tipping pencil. And we can incorporate dissipative forces into this framework by simply considering that the energy, this total energy which is constant with just conservative forces, will slowly decline with time as or I should say, it can decline or increase. It depends how the work term is computed. But if we have dissipative terms, that energy will decline with time, which will, for example, change our constraints or change the sort of energy, the kinetic energy, as this object is moving around the system. So make use of these energy diagrams both for computing and also visualizing your motion. They will help you sort of understand what's going on with systems even when they're much more complicated than we can solve with, for example, force and Newtonian motion.